This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Diomidis Spinellis for Software Engineering Radio. Today I have with me Kirk Pepperdine, and I will be talking with him on performance optimization. Kirk Pepperdine has been working in high performance and distributed computing for nearly 20 years. His focus has primarily been on performance, working on architecting, developing, and tuning applications running on Cray and other high-performance computing platforms. Kirk now specializes in Java, where he works in all aspects of performance and tuning in each phase of a project lifecycle. Kirk was recognized in 2006 as Java Champion. Kirk, welcome to Software Engineering Radio.
Thank you for having me here.
So, where should developers encountering a performance problem start their investigation?
That's always a good question. A lot of people have trouble, knowing where to start. They get a lot of confusing information from a lot of different sources, and it really takes some time to understand what all of this information means and put it into some context so it all makes sense. Because generally what I find is that all of the information, even the stuff that looks contradictory, tends to make sense, but only after you know what's happening. Prior to you understanding what's going on, it tends to be very, very confusing. So this is one of the reasons why I developed a model, because the model helps me understand what's going on in the system. It basically allows me to take all of these signals, dump it into the model, and then the model helps me make sense of it. So I call this my performance diagnostic model. And
can you briefly describe what it involves?
Well, it's like any other model. The model has something representing all of the components of the system in it, and from that it helps me to understand what each of the components are responsible for and what their interactions are. And so when you run into some performance issue, you can look at the signals, you can put it in, and you can say, okay, which components would possibly be responsible for these types of signals? And each of the components are distinct in the sense that they are responsible for certain sets of signals. And by using this particular model, what I can actually do then is take these signals, plug it in, and it helps me to, from a top-down point of view, tunnel down like through the layers of complexity to get to where the root cause is.
Could you give us a concrete example?
Yeah, sure. Absolutely. I was contacted by this one company just a while ago, and they said, we need to have our garbage collectors tuned. And I said, okay, cool, I can do that. No problem. I need garbage collection logs, because the garbage collection logs are going to provide me with the visibility I need into what the garbage collector is doing. And so, I said, here's how you collect them. They did all that. They sent me the garbage collection log. I started the analysis on the garbage collection log, and I looked at it and it says, garbage collectors are working fine. There's not an issue with the garbage collectors in this particular application. In other words, I could tune the garbage collectors from now till whenever. Things are not going to get better, because that wasn't the primary problem with the application. And
right.
And the garbage collector, the garbage collection logs sort of also act as what I call a proxy metric for other things that are happening in your application. And this falls all under the box of memory. How does your application consume and churn and basically interact with memory, right? Are you memory efficient? Are you memory inefficient? Do you have large live sets? Are they stable? Do you have small live sets? Do you churn a lot? So those types of questions. In this case, what I found was that the application was very memory inefficient. And you can't tune a garbage collector to make up for an application's memory inefficiency. You have to go back to the application and tune it.
So should developers start at a higher level, look at some high-level things first, and then focus on particular areas?
Well, I always ask the question, okay, so what are the SLAs that are being missed? What are the conditions in the environment? So what are the signals that the environment is giving us? And then I'm going to look at look at those conditions, right? So what are the SLAs being missed? Look at the conditions in the environment for the components that are responsible for you meeting those particular SLAs, and I'll use those signals to try to sort out what the root cause is. So in the case of this particular company, I knew I could use the garbage collection log as a proxy measure for certain aspects of application efficiency, and as it turns out, how other aspects of performance, right? So the garbage collection logs can act as a proxy measure of this whole thing. So when I saw that the garbage collector itself seemed to be running fine, then you have to look at the workload. And the workload in this case was enormous. And I said, okay, fine, so we have to go down that route. And the way I got there was by basically saying, I'm going to look at the specific signal, but then I'm going to step back. And when I step back, I'm going to look at the overall picture. And, there are indicators in the garbage collection log that, in this case, help me understand what was going on. That's not always the case, right? But in general, what you want to do is you want to get down to some key core metrics. And you want to use those key core metrics to help you get an understanding of what the overall condition is in the runtime that's causing the problem. And then use that information to basically tunnel down or focus on identifying what the problem is.
What could these metrics be?
Well, most of them are just simply hardware metrics, and these are really cheap and easy to get. So one of the things I do is I identify what I call the dominating consumer of the CPU. That activity or the condition inside the CPU that's dominating how the CPU can be consumed. And you get into two different conditions. You get into passive dominance, and you'll get into aggressive dominance.
Such as?
Yeah, well, passive dominance is the harder one for people to recognize and the one that they miss out on most often. But it's some condition in the runtime that's preventing the CPU from being consumed. So if I've identified passive dominance as being a problem, then I'm going to look for conditions that could cause the runtime to prevent the CPU from being consumed. And of course, aggressive dominance, as you can imagine from that definition, is that I am just doing something that's just basically saturating the CPU.
Could you give us some concrete examples so that people can relate to them?
Yeah, here's a simple one. I have an undersized thread pool in my application server. Okay. I have a whole pile of requests coming in. And so, where's the block? Well, I can't get a thread to be processed. And they can't get a thread to be processed because, there just simply aren't enough threads in the thread pool. When you look at the hardware under those conditions, what you're going to see is that the hardware is being underutilized. So what I have are exceptionally long response times. If you look at the time budget on the thread, you're going to see that the majority of the time budget is going to be spent in the thread pool, basically just blocked waiting to get a thread, right?
Right.
And you're going to see the hardware is underutilized. Let's flip that around.
Exactly. What's the other case?
Well, not the other case. Let's flip it around. And, what does that look like to, like an operations person that's looking at their application? They see they're not meeting the SLA, so they have SLA violations, and they don't know why, right? So what is the information that they have that can lead them to the path of understanding that their thread pool size needs to be increased? Well, generally it's going to be look at the hardware counters, and you're going to see that I have all of this load coming in onto the system, but my CPUs are underutilized. And that's usually some signal of some congestion someplace. And in this case, there's a very easy trick to discover what's going on. And that's simply do a thread dump. And when you look at the thread dump, you're going to see that all of the threads in the thread pool, or the connection pool, or, database pool, or, whatever it is, whatever the pool is, they're all going to be busy, right, doing something. And if you see that all of the threads in your thread pool are always busy doing something, then that's a pretty clear indication that it's undersized.
I see. Are there particular tools you recommend for getting these details?
Yeah, sure. And these are like really cheap and easy. I can use JCMD, free tool, comes with the JDK, right? So if I do just J command on the command line, it gives me a list of all the JVMs I can communicate with. If I do a -- help, it, with the PID of the JVM of interest, it tells me all the operations that JVM will support. One of them will be, print stack dump, and I can just execute it. And after that, it's a text file. So there's tools like TDA, which you can use. It's a thread dump analysis tool. And, just load the data into that, and you can just splunk around and just simply be curious. That's all. You have the data, be curious.
So you're assuming the application is multi-threaded, but that's not always the case. So when the application is not multi-threaded, you have to start from a different perspective, I assume.
Well, you have to adjust the model. Again, you have to look at it, and we've worked with applications that are purposely single-threaded, right? So event comes in, event loop takes event, processes it type thing, but it's always single-threaded. I've done this on a number of occasions. So you have to adjust the model. You have to look at this and say, okay, this is single-threaded by nature. So in one case, we had a 24-core box. We're using like one core for processing, single-threaded. We just adjust the model and say, okay, single-threaded, I can only consume one CPU. So I'm going to just adjust the model and say, okay, based that I'm using only one CPU, let's do the exact same analysis. Am I able to consume that CPU or am I not?
Mm-hmm. And you often say that you are consuming it or that you are waiting, and then how do you proceed from that point onwards to find the real culprit?
Well, that depends on if I'm consuming it or if I'm waiting it. If I'm consuming it, then I have an algorithmic strength issue. And then what I have to do is I have to find some way to reduce the algorithmic strength. Now, that could come from the garbage collector is overactive. That could come from the application is memory inefficient. That could come from just, the algorithms I'm using are just, too expensive. And I need to find something that's, I need to go through some strength reduction in that case in order to try to do something. In one case, we looked at the workflow and we said, some of this work doesn't need to be done all the time.
Mm-hmm.
So we took it out. And that's cool because, shorter execution paths take less time to execute. So simply doing less was the answer. Now, we added new events to the system to do the stuff that needed to be done occasionally. And in that case, that helped quite a bit. It took, in this case, it took the idle loop and made it, 2 to 3% more idle, which is good because we wanted all of the incoming events to be executed almost immediately. The only way you're going to have something executed almost immediately or immediately is to have a waiting thread for it. If you only have one thread, that means that one thread needs to spend a lot of its time being idle.
I see. And somehow you can also adjust this model, I assume, for applications that deal mostly with network calls, for example, REST applications.
Yeah. In those cases, the model also works in this case because you'll see indications that you're too reliant on the network, or there's I guess the common performance anti-pattern is what's known as revolving door. And revolving door is basically, well, it comes from EJB, right? Where we had a client, NAD bean or whatever, session bean, whatever, it doesn't matter. But you basically have a client and a server, and you need to get the data from the server. So I'm just going to do like get X, get Y, get Z, and so on. So I make all of these really, 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 really small network calls. And of course, that's going to put a lot of stress on the kernel. So that's going to pop the kernel times. And you can see that in the CPU counters. Another common thing is Hibernate and what's known as ripple loading. And that's really a case where you should do like you're essentially doing a table join, right? Mm-hmm. And you probably should do the table join in the database, but what Hibernate is going to do is it's going to basically do select star from table X for every element in table X, select select data from table Y and join it in memory, right?
Right.
So this is like a revolving door pattern. So I'm just and of course the duration is linear to the size of table X. The number of calls you make, right? So you get all kinds of like bad things happening in terms of performance, but the big telltale sign is that you're going to really hammer the kernel, and the kernel's not going to like this. And if you hammer the kernel, you are going to limit the scalability of your application. And in this case, if you consider that every network call takes a millisecond, and you do 1,000 of these, then you have a floor on your response time, which is, in this case, 1 second. And quite often we don't see that it's like, 1,000 calls. It's generally more like 100,000 calls or, something larger than that, which means that, the response times now are hundreds of seconds.
Right. So let me switch to the role of databases. Would you look at the database performance from the database side or from the application side? Where would you begin to look at things?
Here's where you start getting confusing information. If you have a good database guy and he knows what he's doing, what you're going to find is that he's going to come back to you in these cases and say, look, guys, we're clearing transactions, without any issue. No problems on our part, right? But, of course, you're going to have your end users saying like, but, and probably a lot of the metrics are going to say, yeah, it's a database problem. But is it really a database problem if you're trying to make 100,000 calls when all you really need to do is issue a join and get the results you want, right? This isn't saying, write your business logic in SQL. It just basically means, you have to still be intelligent about the number of network calls that you're making because that is an expensive resource and, yada, yada, yada about network stuff. All that aside, database performance is generally very, very, very good. Databases are generally not a performance issue if you use them properly. In this case, Hibernate ripple loading is a perfect example of how to abuse the database. And you're not really abusing the database. What you're doing is you're abusing your network stack.
Right. So are object relational mapping approaches part of the problem or part of the solution? What's your experience in this? Yes, you mentioned Hibernate.
Hibernate's a good product. It solves a particular issue, and if it's used properly and people understand it who use it, then I don't have any issues with Hibernate. It's got its issues, of course, and you have to do all kinds of wacky things to deal with the issues. But that's not Hibernate's fault. That's basically trying to get around the problem that we don't have a real good global identity system for object systems, and that's a completely different topic.
Yeah, we can talk about architecture a bit later on.
Yeah, well, that even goes beyond architecture. That's just, I've talked about this in microservices talks, but, if you need to maintain the property of singularity in your systems, then you need to have proper identity. And as soon as you do distributed computing, you lose identity, which means you lose singularity, which means that you pick up a whole host of problems because of that. Hibernate just makes it a lot easier for the uninitiative to run into this problem.
One last thing regarding databases. Often colleagues tell me that they have a not so clear database schema, not normalized in order to achieve high performance, but then the database schema suffers. So how do you resolve this tension between a clear database schema and high performance?
In my experience, I've not really seen this happen. In other words, if you have a good database person and you come to them and say, look, this is what we're trying to do, generally they'll come up with a schema with the appropriate indexing that will result in the database not being an issue. In the few cases where it is an issue, caching is your friend.
Mm-hmm. At the application side, right?
Yes, on the application side, obviously, and there's some very, very good products that are able to do this. You know, I don't want to mention any of them because the other guys will get upset. But you know, there's, but in general, I mean, they all come with their pluses and their minuses. But in general, they all do a good job of, if something is expensive to acquire, then the obvious answer is cache it if you can.
I see. Okay, we can discuss now architecture. So how important is software architecture for an application's performance? You mentioned this global identity, but I assume there are wider issues here.
It's critical for performance. If you don't come up with a good solid basis from the beginning, then it's very likely that your system will never perform no matter what you do to it. You know, in my mind, just really taking care to look at architecture from the beginning is kind of important. And I know that sounds sort of non-agile, but I would tend to disagree. I think that if you look at some of the more well-architected systems that are out there today, these shops are very agile. And, agile doesn't mean, Scrum's agile and all of this other stuff doesn't mean we don't plan. It just means that we plan in a different way, right? Mm-hmm. So all of this work has to fit into some sort of framework, and that's generally what we call architecture. So there must be some architectural goals in mind when you start. Now, you might have to be flexible on some of these, but in general, some of the more modern architectures, certainly the type of architectures that microservices and cloud environments are favoring, in my experience, have tended to be the most scalable and the most performant for most classes of problems. Not all, but most classes of problems, if they're done properly.
Isn't there a danger to over-architect or to architect in the wrong direction if you start thinking about performance from day one?
Yeah, it's kind of funny. There's certain things that you want to consider when you're architecting, but I think the first thing you need to do is make sure that you have a functional product. Having the fastest app on the planet that no one uses isn't very useful.
Obviously, yes.
Right. In my mind, I mean, even the stuff I write, I'm going to use architectural designs that I know are going to help me tune this thing if I need to tune it. But generally, performance is a secondary concern when I'm starting off in a project. If I've architected it so that I can do things to the application afterwards easily, then I'm going to be satisfied with that. So some of the things, follow good coding principles. Make sure the things that are coupled, that need to be coupled, are coupled. Make sure the things that should be loosely coupled are loosely coupled. Worry about complexity. Those are the two biggest things I think that people should take away. Tuning is a debugging process. You have a regression, a performance regression. Mm-hmm. Somebody's going to have to go in there and refactor code.
So you want to make it easier for them from the architectural point of view.
Okay. I have a bug, 1 + 1 = 3. I need to go find it. Same issue, isn't it? Really?
And regarding particular architectural choices such as the JVM or containers or microservices, how do you think they affect performance? You mentioned microservices, I think, as a good thing. Are they always working like that? I assume some have overheads associated with them.
Yeah, of course, they actually do. Again, we don't have what I would call a global identity system. So as we punch data around clusters, we do a number of horrible things. One of the horrible things we do is we have basically copies of data, and copies of the same thing. So we've lost singularity and we've lost identity on a cluster-wide basis. So that's an issue, right? But that's a consistency issue more than a performance issue. The performance issues come when we pass data around. The most common scheme to pass data around these days is JSON, right? And we're using an incredibly sparse representation of our data. So that means takes up a lot of space, and we're using some very expensive, or probably the most expensive resources in our system in order to push this data around. I think of it this way, right? If it takes me like a millisecond to get a message from one service to another, right? So, and a millisecond is a good thing. I mean, you also have a lot of other what I call ancillary effects in the act of getting the data from one place to another. If you have even a 2 gigahertz processor sitting in your machine, my question is, how many operations can you complete in 1 millisecond with that processor?
It's not something to be sneered.
No, absolutely not. So the decision to offload the processing to another service or consume it yourself, or just do it yourself, I mean, you have to look at it and you have to answer that question. Is it worth distributing this particular message, or should I just do this myself? And what are the consequences of each choice?
So you're saying that microservices, you can overdo the amount of splitting you do. Is this what you're getting at?
Well, microservices is an architectural style and a way of doing things. So there's all kinds of things that help people. It's basically a way of operations, as not just an architectural style, right? So, but from an architectural style point of view, then, it's the same as any other distributed system. Yeah, you can easily get into a revolving door effect.
But applied carefully, they can help towards achieving better efficiency.
Applied carefully, they're amazing. It's the first large service-based architecture that I worked on was a number of years ago. And at that time, the architecture really came because we just didn't have any other way. I mean, you could not stovepipe this application. It just wouldn't work. So, that service-oriented architecture really came out of a necessity. It was the only way that we could do things. But when we're passing data around, we're passing around big chunks of data that took significant amounts of time to process. And, because of that, we didn't really have any of these, we didn't have good networks, not like today, but we didn't suffer from any of the problems that you would have because of, all of the network activity, mostly because the proportion of network activity to, computation was just so high that the network was below the noise floor in the equation, right? And I think that's really one thing you want to make sure is you want to make sure that the network noise is in the noise floor in terms of the overall computational costs.
Because it's overhead, right?
Yeah, it's just pure overhead, absolutely pure overhead, and you want to try to amortize that cost. So if you do it that way, you can get amazing results, absolutely amazing. We were also event-driven. And event-driven, and this was in the era before, we didn't call it SOA or micro
Reactive.
or anything like that because we didn't have those words to describe what we were doing, Yeah, these words just simply didn't exist. But we had a lot of the same concepts. Obviously, the tools today are different and better, and microservices, in terms of a philosophy or a way of getting things done, didn't exist. So we didn't have any of those tools. So I can't really call it microservices, but it was certainly SOA. And the benefits of that particular architecture, being event-driven, service-oriented, have basically stuck with me, since that time. And to see this, trend emerging where we have like event-driven designs and large SOA-based applications and now microservices, to me just seems like a natural progression from a lot of the lessons that we learned in our particular application. It just makes your system so much more flexibility. It puts you into a position where you can actually experiment with different things. You can run the experiments faster at a greater rate. You can do them in your production environments, not in test environments where you're going to get it wrong. The advantages just go on and on and on. So for, I would say, the vast majority of applications on the planet, this type of architecture is just, the bee's knees, as they say.
So this is something our listeners should remember. You mentioned earlier garbage collection, which brings it to the topic of programming languages. So people often claim that a specific programming language is less efficient than other. I had the discussion regarding our show with a colleague who told me a case where Rails was 100 times more expensive than production setting than a JVM alternative. So should the underlying language be a primary concern when choosing applications platform?
No. I don't think so. I think people are, when they focus on performance, they're actually focusing on the wrong thing. Mm-hmm. You have to look at, what's expensive in deploying a system, what takes time, where are the problems coming from. And most of the problems are coming from developers being unable to express themselves in code, right? Now, is that a problem of the developers? You could argue yes, but will also argue no. So I'm going to take the no side here. Not a problem of developers. It's a problem of the language's ability to allow the developer to express himself.
Uh-huh.
Okay.
Can you give us an example?
Yeah, off the top of my head. Well, you can just think of, so let's go back. Prior to Java, prior to JEE, prior to all of these things, distributed computing was the realm of, high-performing specialty teams, not a day-to-day, everyday developer. Post-Java, distributed systems are normal, and even mediocre developers are building distributed systems. You may ask why. In my opinion, it's because of the languages and the tooling and JEE and all of these things that have allowed the developers to become more expressive. That's what's important. They're more productive. They're building larger systems than they could before. And you don't need a team of rock star developers to get interesting things done. Normal people or normal developers can work on problems that were unreachable even, 15 years ago.
So you're saying there is an effect of the language, but it has more to do with how it allows programmers to express themselves in a higher style that can be more efficient than at low-level details, such as the cost of garbage collection or something like that.
Absolutely. The fact that we have these problems with garbage collectors because of systems doing this, that, or the other thing, we didn't have these problems in the past because people just weren't able to weren't doing the things that they're doing today simply because they didn't have the tools and languages and support that they needed in order to be able to do these things that we consider to be hard, or before they were impossible. And that's what's happening in this industry, right? We make the hard and the difficult easy, and by doing so, we make the impossible possible, and we make the possible less difficult.
And then we see another peak we have to reach. But languages are also improving, I understand, so things that were inefficient in the past are less so. I presume you have seen many improvements in Java implementations over the years?
Yeah, sure. My whipping post has always been how bad logging is in Java, and it's horrible. It is absolutely dreadfully bad. And the Log4j guys did something to make that better. So that got better. I think JE's gotten better over the years. Spring didn't like the early implementations of JE, and it transformed how we write code, So, you see all kinds of improvements coming from all over the place.
Are there also improvements being done at the lower level, at the JVM level?
Oh, yeah, absolutely. Absolutely. As people learn more, they go back in and adjust things. We used to have a big problem with simple things that people wouldn't even think of called nepotism inside the JVM, inside the JDK classes, and this is where objects get distributed across generations.
Mm-hmm.
And when they get distributed across generations, then you get things that are, you get zombies, because these are objects that are kept live because of the properties of the garbage collector. But these objects are live, but they're not live. They should be garbage collected, but they can't be because of the mechanics of the garbage collector. And so people figured this out, and they've gone back into the JDK and they've made adjustments in the code where these conditions can be adjusted for. And as a developer, you don't have to think about this, because now you can use that data structure and things work better.
So as a developer, what should you think if you are developing Java applications? How can you give the JVM more chances to optimize your code or to work with your code in the most efficient manner?
Write simple code. That's the best thing you can do.
Those 3 words.
Write simple code. It is something that many of us have been saying now for
decades.
Almost forever. Write simple code. Right?
So there's no need to think about the internals or what happens in specific cases. Just write the most simple and readable code you can think of.
That's exactly right. Pay attention to the APIs. Make sure you're writing good, stable APIs that don't cause other people to do bad things in order to have to use your API.
In talking about APIs, we can discuss a bit about algorithms. So nowadays, most algorithms can package in libraries, or system software use a database or data structures. Does this mean that developers will rarely, if ever, need to implement algorithmic code? Have we left the world of algorithms, the time of algorithms, that we need to think about them?
As far as implementation goes, I'm not sure we're ever going to leave them behind. Certainly, we spend less of our time on writing technical infrastructure, such as different algorithms for doing different sorts and things like that. And
that's what I was thinking.
Yeah, in general, that's a good thing, because I'm either writing sorting code or I'm writing business logic. And of course, the thing that's going to bring value to my employer is going to be the business logic. Right. So the more time I spend there, as opposed to spending writing, technical infrastructure, then, of course, that's going to be a win. So yes, we are spending less and less time thinking about algorithms and things like that, like sorting and stuff like that. But I don't think we're ever going to get rid of it. I think, as technology progresses, there's going to be new things that we can do to make things better, which means that we'll have to dive back into algorithms to adjust the algorithms so that they make better use of the new features that are presented even in hardware.
Then developers should still know about algorithmic complexity and take it into account.
Oh, just because they don't have to write it doesn't mean they shouldn't know about it. I mean, you should know what it means when you decide to use a linked list over an array list. You should know fundamentally what the differences are. Right. You should know fundamentally what the differences are and what the implications of using either one are in terms of performance, right? So you can choose the best data structure for the problem. So data layouts, again, for most applications, this has marginal benefits. I know like people like Martin Thompson would be just cringing when he hears me say this. And I completely get what he's saying. He says, the industry is hugely wasteful. And on one end it is. We're hugely wasteful of computing resources. And we can do tons better in terms of coming up with better data structure layouts in order to make more efficient use of our hardware. But I don't think that's the point. I think the real constraining resource is people. And we need to figure out better ways to make use of our people resources. And if that means that we're going to throw away hardware to do it, well, sorry, Martin, but I value people more than hardware.
All right. This is a very interesting view, and we can discuss more
I'm not
about
sure that Martin,
yes.
Yeah, I'm not sure that Martin will disagree with me on that particular point. So don't take this to be trolling Martin. I have a lot of respect for him. The guy is incredibly clever, and people absolutely need to listen to him and take into account his mechanical sympathy movement. I think it's a fantastic thing that what he's done in bringing this out. So I don't want that to be taken the wrong way.
You mentioned throwing hardware resources, which brings me to a discussion about hardware architecture. Over the past years, CPU speeds have been stagnant, and we only seen a number of cores increasing. Will this mean we get more emphasis on code performance? We can no longer expect our mistakes or inefficiencies in the code to be plastered over through higher CPU speeds?
Okay, so I'm going to go back to quoting Martin here, but this time in a good way. He did a study, which I found very interesting. He says, in 2005, clock speeds flattened out, and therefore, we went to taking all of the gates that we can put onto a chip, and we started getting them to do something else. We didn't actually add more cores, but that's a different story. There's a reason why we didn't add more cores. Well, as some people say, before I give you 2 cores, you should learn how to use 1, right?
Right.
Well, so they've given us basically, for all intents and purposes, 8 cores on a laptop, and, how many people actually use all 8? So we don't need more cores. What we actually need is faster memory, and memory is really the huge bottleneck. But that said, Martin did this very interesting experiment, and it was very clever of him to be able to do this. He took an application and got a whole bunch of different generations of different CPUs, and he ran that application on all of these CPUs. And what he found is that the retirement rates for CPU instructions actually was still following Moore's law against all of these CPUs, even though the clock rates were the same.
Because they were getting more parallelism at the lower levels of the CPU implementation.
The CPU's internals themselves were getting faster in some cases. They were getting smarter in terms of being able to provide better optimizations, and they were getting more parallelism, so they were able to do more things at the same time. So, and they were doing a whole bunch of other things. But effectively, the CPUs are just getting better, even though they're not getting faster. And we don't know, I don't personally know when this is going to end. I don't follow CPUs as much as Martin does, so you can ask him that when you talk to him. But to me, I don't think CPU power, and in my experience, CPU power hasn't been an issue for 15 years or more.
You mentioned memory that is not keeping pace, but we have another type of memory. So secondary memory is improving dramatically over the years with SSD and similar technologies.
Yeah,
does this affect application performance? Is this something we should take into account? How we tune, how we devise architectures for secondary memory?
You still got a problem. You got to get the data from that thing that's very, very far away to someplace close, right? Like you got to get it into the CPU. And so the primary bottleneck is and always has been, getting it from memory into the CPU, or right, getting it off the bus into the CPU. And as you can see, that bus clock speed hasn't really been changing until recently. We had a jump, but prior to that, it's been fairly constant. If you look at, disk performance, then compared to SSD performance, generally it's better for a lot of cases. But I did a test with a guy a while back. I basically said, here, we both have the same movie, i.e. big file. I said, let's just copy it. You have a hard disk, right? I have an SSD. Let's dupe it. And we'll just see who gets the cursor back first.
Right.
And the cursor came back close enough on both machines that I wasn't able to say that the SSD was faster than the hard disk or the hard disk was faster than the SSD.
But that was sequential access.
That was a sequential access.
Random access, that's where an SSD can excel, no?
It depends. And you can find in non-sequential access that sometimes the hard disk will do almost as well as an SSD. It's sort of non-intuitive. So I don't think that these things are really making a difference in terms of how you should think about your application. You should just think of it that I'm going to do an I/O operation. And my path from my application down to whatever device it is this long. It's yay long. I go through, an application buffer, maybe several application buffers, depending on how we marshal the data down, to finally to an OS buffer, to maybe some internal disk buffers, to finally maybe I get onto the drive, be it SSD or not SSD, right? And so if you look at that, that tends to be what I would call the dominating cost in the entire process.
And this will always be expensive.
And this will always be expensive. Right.
One other thing we can do is load lots of data nowadays into RAM. We have tens of gigabytes of RAM, so that's another alternative rather than doing disk processing. Is this an avenue that strikes you as interesting?
That's a very interesting avenue. Actually, it's a funny one too. The coherence guys set up a cluster where no machine in the cluster had a disk, right? And you might think of this like, okay, well, that's crazy. How do you persist everything, right? And the answer was nothing was persisted, which might seem risky. But
I wouldn't want my bank to do that.
What's that?
I wouldn't want my bank to do that.
Actually, it was a bank doing it.
Okay, tell us more.
And so, and here's the reality of the situation. You're going like, whoa, no, you don't want to do that. And it's like going like, well, let's do some math on this. First off, they had everything replicated, and they had it partitioned. So the data was all replicated multiple times, and it was partitioned, and they had things to basically make sure everything was in sync. They had the power lines, basically all set up so that even if they had multiple failures on power, everything would be okay. And, when it finally got to the hardware, they just took the disk out. And what they found is that made the hardware more reliable in the sense that they had fewer failures, which actually makes sense because if you think about the most failure-prone component on your system,
it's a mechanical one.
The disk, even the SSDs, right? SSDs wear and they have all kinds of problems. Okay, so cool. So we just took the most unstable component out of the computer. So what does that do to the reliability numbers? Increases them, yeah?
Yes.
Problem solved. Not as crazy as you think.
Main memory computation is something that you think is a way forward for some types of applications, correct?
Yeah, I think until we solve the memory CPU bottleneck issue, which will be solved. Yeah, keeping stuff in memory, keeping it in cache, improving cache line densities. And there's a whole bunch of different things like that I think will be essential if you're at the high-end performance, high performance end of the spectrum. For most applications, it's these types of issues are not important because you have other things that are just much bigger consumers of the overall time budget.
Let's close with some overall discussion. So, what's the number one mistakes developers do regarding optimization, which is something that you often see?
Just optimizing prematurely, making. I can just give you an example. We were working on a pricing engine once, and the guys responsible for the internal algorithm realized it needed to be super, 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 super fast. But we didn't have proper requirements from the customer also. So they went into Donald Knuth's, wonderful data structure books and pulled out this quad tree complicated thingy, and they're basically scratching their heads, trying to figure out how to implement this exceptionally complex data structure. And I looked at them and I said, you guys are crazy. Our first implementation should be throwaway because we don't have requirements.
Mm-hmm.
And because we don't have requirements, anything we give them is going to be wrong. But by giving them something, they're gonna tell us what's wrong. And afterwards, if we need that thing to go fast, and we have all the requirements, then we can look at implementing the ultra expensive, complex, funky quad tree thing.
To satisfy the SLAs you mentioned earlier on.
To satisfy the SLAs, assuming the simple implementation didn't do it.
Mm-hmm. Mm-hmm. And on the converse side, what's the optimization that delivers the most positive results? So where should people start? Or what's giving the most bang for the buck?
It depends on what your problem is. Generally, some things that people miss is they don't do a proper GC tuning. As soon as you deploy, you should have something built into the schedule that basically says, now we need to tune the garbage collectors. So that's probably the simple thing that people miss. They don't realize. That
should be an obligatory step.
I think so. After a deployment, it's sort of like one of the last configurations you do is you just say, okay, now how's the garbage collector performing, and what can we do to cope with that? The one topic we haven't touched about, and possibly is kind of interesting, is where we consider the future of performance tuning and what future tooling would look like.
Mm-hmm.
And this is where we actually see artificial intelligence actually starting to play an important role. So this is something that we've actually been working on for a number of years now, is how do we make diagnostic engines that are intelligent and can adapt to conditions, do diagnosis of when problems appear, that are much more complete than what you get with a simple profilers and things like that. We want these things to be able to run in production environments. We need them to be able to run in toxic environments. So this is what we've been working on.
Would you trust them to do that?
Not only do we trust them, we have several customers that are trusting them to do this. And we've been finding interesting problems that we didn't recognize that, or didn't consider that the engine would actually pick up on. And our engine is still what I would call fairly immature. So, I mean, if you stack us up against a traditional tool, we come up very light, currently in terms of features, but we're slowly building this thing out. And what we're finding is that, we, with the proper modeling and the proper model in front, we can apply AI techniques and numerical analysis techniques to systems, and we can actually come up with very, very good diagnosis of performance regressions, generally in less than 20 seconds. So something that might take me an hour or so, assuming all of the tools and the environments cooperate to diagnose, generally our tooling can find that within about 20 seconds.
This sounds like an exciting development.
92% of the time.
All right. Kirk, thank you very much for being with us. Where can listeners find more about the topics we discussed?
Well, we run a blog at JClarity. We have friends of JClarity. So since I mentioned Martin here, I guess I need to give his mailing list a plug, which is Mechanical Sympathy. I think you'll find that there's a ton of really smart people on his list, as well as ours. I think a lot of them participate in both lists. And get involved with OpenJDK. If you're monitoring the mailing list, then you're going to see what's going on at that level, which can often be helpful.
Thank you very much again.
Thank you for having me.
This is Diomidis Spinellis for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.